All right, so I guess for everyone who's watching the recording, what I went over very briefly was write through caches and write back caches. And essentially the difference between these two is one of them, whenever you do a store word, it always writes back to memory, while the other, a write back cache, only writes back to memory when the cache is evicted from the cache line. All right, so now that everyone's up to speed, we're gonna go over this first problem. So how many bits of the address are used for the block offset? Can anyone who is present in the discussion answer? Yeah, can I show the values again? So I'm not sure if you can see it super well, but in the top right, the total size is 16 bits or 16 bytes. And then our block size is 4 bytes. And then it uses least recently used and allocate and write back. Those two last two things are probably not super relevant to the block offset bits. Yeah, so it is 2. And the reasoning for that is because, so we have 4 things in our block offset, right? Or we have 4 things in our block. We have 4 bytes in our block. And to count each of those individual things, we need 2 bits. So like to count like 0 to 3 with binary, we just need those 2 bits. We can do 0, 0, 0, 1, 1, 0, and 1, 1. And that's 4 different things. So we have a way to address all of the individual bytes in our block. So now that we know the block offset bits, how many bits are in our tag? Yeah, 14. And how did you get that? Yeah, 2 bits for the offset, and our total address size was 16 bytes. And then now, how many total blocks do we have in our cache? Yep, we have 4 blocks in our total cache. And now, how do we go about calculating our overhead bits? Well, back here, we know that our overhead bits are the valid bits, the dirty bits, the LRU, and the tag. So we already know how many bits are in our tag, and we know that valid and dirty only are going to need 1 bit each. So the question is, how many bits are in our LRU? So 2 bits in our LRU. Yep, that's correct. And the reasoning why we have 2 LRU bits is because we have 4 blocks, and that's how many bits we need to address 4 things. So our total number of bits is 18. And I think, yep. Oh, sorry. So our overhead bits is equal to 18. And then the total number of bits, since we have those 4 blocks, we actually have 4 of these lines, right? So each of these, if each of these is 18 bits, or 18 bits each, and we have 4 of them, we have a total of 72 bits. So that's where they got that last value. All right, now let's go over the second question. So now part 2 of the discussion is the number of sets per cache. And can we organize our caches further? Our current structure works well for smaller caches, but imagine if we had 128 blocks that we don't want to search through all of them. So basically what this question is posing is, let's assume we have a cache that's pretty large. And also, if we were just using the structure where each individual, like we have no organization except for looking at a block, right? So each block has its own tag. And is that maybe the most effective way? Or can we maybe organize our cache a little more cleanly and maybe, I guess, better? So what if we had restricted certain blocks to only be in certain sections of our cache, just like organizing books by category or alphabetically? And what we can do is we can use the next S bits after the offset to determine which set or category a block is in. So as you can see, we have our block offset here. And then we have a set index in the next set of bits. And then we have our tag. So the really important thing to understand about this is we're kind of using two things of organization for our cache now. We're using a block offset to determine which byte in our block we're grabbing. And then we're using a set index to determine which way in a set we're grabbing. And a way is just like a cache line in a set. And we'll get into further detail about that in the next slide. So as you can see, we can vary the number of sets in a cache, and we can kind of divide up how a cache works with the number of sets. So the classic fully associative cache we've been talking about has one set, it's the entire cache. And the number of set bits, because of that, is 0, because we don't need, the number of bits we need to index into one thing is 0, because we're always going to be using the same thing. And the number of ways is the number of things in the set. And since we have n lines in our set, so one line would be this, and we have n of those, that means the number of ways in our set is n. And I think the next part, the set associative cache on the middle, I think this illustrates the idea of ways the best. So as we can see, we have set 0 and set 1. And each of those have two ways, meaning that they have two separate lines. So in set 0, you can see we have way 0 and also way 1. This means if tag is, let's say we have two tags in our cache, and they're both associated with the set 0. Because we have way 0 and way 1, we can fit both of them in our cache. And then finally, we have a direct map cache. This is kind of the most restrictive cache, and the number of ways per set, the number of ways is 1, and the number of sets we have is correlated with the number of lines we have. So as you can see, in this cache, we have 4 lines and we have 4 sets. And the really important, why the number of set bits is n. So yeah, sure. So the number of sets we have is 2 to the n, right? So the number of ways, the number of bits we need to address 2 to the n things is we need to have n bits. So let's say, for example, we had 2 squared sets, which is equal to 4. In order to index into 4 different objects, we need 2 bits. And then a really important concept to know for project 4 is that the number, direct map, set associative, and fully associative, the only really big difference is the number of sets they have. They're not like wholly unique caches. The direct map has the most restrictive number of sets, and the fully associative has the least restrictive number of sets. So does anyone have any further questions on what I just went over? Can you explain ways again? Yeah, for sure. So so basically what a way is in our set. So let's take, for example, our fully associative cache. A way is just this individual like block with the individual cache line with its block. So we know that each cache block has a tag along with some data, right? So right here, in like the one I circled, we have a tag along with 2 cache blocks. So that would just be considered one way. Did that answer your question? And then what about the set associative? So the important thing about set associative is first, we divide our cache into sets. So in this example, we divided it into 2 sets. Then, because we divided it into 2 sets, each set, we have to count the number of ways. It's basically saying how many blocks are in a set, right? So in this example, since we have a total cache size of 4, and we have 2 sets, that means each set has 2 different ways in it. Does that, okay, cool. All right, so now let's go over the second question, where do the blocks end up? So for this question, we're imagining we have an 8-bit byte addressable architecture, and we are testing 3 different 8-byte caches, which we saw on the previous slide, basically just these 3 things. Where do the following, and our cache has the following specifications. Cache number 1 is fully associative with 2 byte blocks. Cache number 2 is two-way set associative with 2-byte blocks. And cache 3 is direct maps. Where do the reads to the following address end up in each of our caches? And we're assuming that each cache is initially empty. So because they're initially empty, we know that this read is going to have to be a miss. So we're going to see which block it fetches. So for the first one, we know, for the first thing, my first question for all of you is, how many bytes are going to be used for block offset and set index for the fully associative cache? Yep. So because our blocks are 2 bytes each, that means we just need 1 bit to count them. So that means we have a 1-bit block offset. So that, and do we need to care about set index for fully associative cache? No, you're correct. So that means our tag is just this number with the last bit cut off. So that means we're going to look up 0B10011011. And that is just going to be, let's see. All right, so can anyone tell me why we address the first object with this tag? Right, so we just need to get rid of that lowest bit, and we need to get the tag as being 10011011. So at least the thing I'm a little confused about, which is really bad, is I don't know why that tag is associated with the very first object. Which bits does it grab for? Okay, give me a second. Yeah, so why is it stored in the first line? Oh, okay, yeah. The reason why it's stored in the first line is literally because it's the only object in our cache. That's my bad. Yeah, it's arbitrary. All right, so next question. So what would our block offset be for the second one, along with its set index? Yep, our block offset is still 1. And what would our set index be in this case? And if we're addressing into 2 things, how many bits do we need to do that with? Yeah, so our block offset is still 1, and our set bit is also 1 because we have 2 sets. So that means our address is going to look like the following: 1, 0, 0, 1, 0. I don't think I can squeeze that in. All right, and now this is where it actually goes matters a little bit. So which set would this tag be in? Yep, it's in blue set 1. So like we kind of learned from the last time, the area inside the set is kind of arbitrary, but the actual set matters because of the set index. So we could choose way 0 or way 1 in set 1. It's just arbitrary. Now for the final question, our block offset we know is 1. What's our set index for this question? Yeah, so this time, since we have 4 sets, we'd have a set index that takes 2 bits, or I guess line index in this case. So that means our new tag is 1, 0, 0, 1, 0, and then 1, 1, 1. So which line should this go in? Or which set should this go in? The last one? Yeah, so I kind of gave away the answer there, but this tag should be placed in the last cache, in the 3rd set. And then we can scroll down and, yay, we got all the answers right. So now for the last question, we're gonna go over 3 C's of cache misses. So what is 3 C's? So 3 C's is a way of organizing cache misses to kind of see where we can make improvements to our cache. And it's a way of classifying misses we run on accesses on our cache. And based on these classifications, we can draw some conclusions about what our cache is good at and what our cache isn't good at. So we use 3 C's to classify misses, and we run accesses on our cache as well we also run accesses on an imaginary infinitely sized cache and a fully associative cache of the same size to make our comparisons. So it's basically a way of benchmarking our cache. However, the 3 C's of cache misses is a little phony, as they don't always help us improve our cache, but it's a good guideline to use. So there are 3 classifications of cache misses. First, we have a compulsory miss. So when we benchmark our cache and our infinite cache misses, that means every single other type of cache has to miss. But increasing the block size can help this. And can anyone kind of explain why increasing the block size may decrease the number of cache misses for an infinite cache? This is a little more conceptual for a cache. Yeah, so to give you guys a hint, let's say we had a cache that had a block size of, let's say we had 2 caches, cache A and cache B. And let's say cache A had a block size of 2 bytes, while cache B had a block size of 4 bytes. And we have the following memory. And let's say we do a memory access of 0. And is it because we are able to store more entries, so if we're able to hold more data, then we have a bigger chance of getting a hit? Yeah, kind of. So the main reason why increasing the block size can help is because if cache B pulls in address 0, that means it pulls in every single part of this data, right? While if cache A pulls in address 0, it only pulls in addresses 0 and 1. So that means if we were to do an access on address 3, in cache B, that would be a hit. However, in cache A, that would be a miss. So I think Brian's answer is pretty on the nose. So the next classification for a cache miss is a capacity miss. So this isn't the case if a fully associative cache misses, and just increasing the cache size can help reduce the number of capacity misses we have. And then finally, we have a conflict miss. So if our cache misses, but the fully associative cache hits, increasing the associativity may help. So increasing the associativity is basically just increasing the set size and the number of ways in our set. And the one important thing to note is that these changes don't always improve our performance. So now we're gonna go over like this pretty long-winded classifying cache misses problem. So we're given the following situation. We have a set associative cache with 2 ways per set. We also have a total size of 8 bytes and a block size of 2 bytes. And we're using the replacement policy LRU and the write policy allocate and write back. And below you'll see that we have a chart with a bunch of addresses, and we're trying to classify hits and misses. So the first thing I'm going to go through is the infinite cache. So I'm actually going to pull up the worksheet now. So we have infinite caches and we have hits and misses. So we know that our block offset, we did this question earlier, our block offset for a fully associative cache of this type, assuming that we don't have our set index, is 1, right? So that means our tags are just going to be the upper 7 bits of our 8-byte or of our 8-bit addresses. So that means for our infinite cache, the first access has to be a miss because it's not in the cache. And now in our infinite cache, we have, just gonna write it down below. So we have the address 000 and then 010. And because address 0x07 is also not it, we're gonna have a miss. And because our infinite cache missed, there's no way a fully associative cache can hit, and it is our actual set associative cache can miss. So that means these misses are also going to be brought over. And these misses are compulsory. Next, we have the access 0x15, and the address for that is going to be 000, 011, and then we also have 000, 1010. So these are the 3 addresses in our cache, and the one thing to note is they've all been misses. Next, we have the access 001, 011, and that's also a miss. And then now we have the memory access 0x17. And note, since we pulled in the address 0x16, that's going to be a hit for our infinite cache. And that's just gonna hit this address. And then next we have the address 0x14. And since we have an infinite cache, the important thing to note is that we don't actually evict any data from our cache. So we can store every single one of these tags. So now, since we have the address 0x14, we get a hit from the address 0x15. And then now when we access the memory address 00, the important thing to note is that this tag is never in our cache. So we have to add it. And now this is where the really important distinction comes from the infinite cache against the fully associative and actual cache. So we know that from the infinite cache, we can just include as many tags as we want, right? However, for the fully associative cache and the actual cache, we know that this is going to look a little different, right? Because we have to evict this first entry. However, for the infinitely sized cache, we don't. So now we're gonna see some differences in the infinite cache and the fully associative cache. So we know that this is a miss, so it has to be brought in the cache. And this is probably where we're gonna see some major changes to our cache. Because the other important thing to note is that in our fully associative cache, since we only had 4 addresses prior to this point, that means, and we only had hits following, that means we only had 4 objects in our cache, meaning that all of these should be misses and all of these should also be hits. So now we're just gonna finish up the infinite caches. So next we have the address 0x05, and because we brought in the address 0x4 up here, That's going to be a hit. And then we have the address 0x07. And since we brought in that address earlier on, that's also going to be a hit. And now we have the address 0x24. And we definitely didn't bring any address that was near that, so that's going to have to be a miss. And then 0x6, since we brought in the address 0x7, that's going to be a hit. And the way I'm doing this pretty quickly is I'm basically truncating off the least significant bit. So basically truncating off the least significant bit means any odd number is, you just take off, like if it's an odd number like 7, you just subtract 1. And then 0x1, since that's odd, we subtract 1, and we get the number 0x0, which we brought in earlier. So that's going to be a hit. And then 0x4, since we brought in 0x5 and 0x4, we're going to have a hit also. And so the really important thing to know about the infinitely sized cache is that any miss in our infinite cache has to be a miss in both our fully associative and our actual cache. So that means you have a miss here, and we also have a miss here. So now I would say the infinite cache is probably the easiest of the 3. The fully associative and the actual cache are probably the hardest. And we can just also label these misses as compulsory. So now let's get into the fully associative cache. And the point we're going to start on is this point right here. After we've read in those 4 addresses and we've had our hits, this is where our cache will look different than the infinite cache because we're adding in the new address 0x00 and we have a miss. So that means we're going to have to do some eviction. So our addresses look like 0000100. And so now our new thing we want to insert is the address 000000. So which element should this be replacing in our fully associative cache if we're using LRU? Yeah, so I think Terry and Brian both said it should be the first element. That's the oldest element in our cache, so that's the element we want to evict. And I think instead of doing a bunch of erasing, I think the easiest way to think about this is kind of like a line. So what we're going to do is we're just going to cross out this element and add the new address we're adding. So that'd be the all zeros. And because that was a miss, our cache now looks like this. So our next access is 0x05. So that means we're looking up this address right here. Do we have that in our cache? No, so we don't have that in our cache. So this is where our fully associative cache and our infinite cache differ. Since we didn't have enough space for that first address 0x04 and it had to be evicted, we now have a cache miss on address 0x05. And then since we had a miss, what do we have to do next? Yep, kick out the LRU and replace it. And what is the block size of fully associative? So the really important thing to know about all these caches is they all have a block size of 2 bytes. And so yeah, kick out the least recently used and replace it. So our least recently used address was 0x07. So we're going to kick that one out and replace it with the address 0x05. So now we're going to do a lookup for 0x07. And as Brian kind of noted, this address has just been kicked out. So it has to be a miss. And because it's a miss, we kick out the least recently used and add it back in. Oh, did they add the wrong thing? Yeah, so I think our cache actually should look like that. Now, 0x24, that's a miss. So we have to add that to our cache and kick out the least recently used. And then finally, we go to 0x06. So is this tag in our cache? Yes, so it is in our cache. We can see it right here. So what we're gonna do is, since this one is a hit, we're gonna update this value and put it as our least, as our highest priority, since we just used it. Next, we have the address 0x01. And is this address in our cache? Or is that tag in our cache? Yes, so that one is also a hit. And then finally, since that was a hit, that means you just update the tag and have it as our highest priority. So now is the last address 0x04 in our cache? Yes, also it is. So that means the rest of the accesses were hits. So as long as you step through it somewhat slow, I don't think these fully associative cache questions are too bad. It's just they're a little tedious. So now, finally, I think what the hardest one is probably the actual cache, because you have to think about how these sets will work out. So, and also we can't really use the trick where we brought over the misses and hits from the infinite cache and fully associative cache, because it could be the case that our actual cache hits while our fully associative cache may have missed, or our actual cache misses while our fully associative cache hits. However, one conclusion we can draw from our fully associative cache is that if our fully associative cache happened to miss, that means our actual cache had to miss too. Because if our fully associative cache didn't have enough space for that element, neither can our actual cache, because our actual cache is more restrictive on which elements go in which sets. So that means since we had a miss here and a miss here, we can bring that miss over to our actual cache. So the only elements you have to look at are these two and these four, the bottom three. So now let's build up our cache again, thinking about this set associativity. And the really important thing to note is, firstly, how many sets do we have in this problem? Yeah, capacity miss, right. I forgot about that. Oh shoot, I'm actually really wrong about that statement I just said. So actually it is possible for a fully associative cache to miss and an actual cache to hit. So what I said here is actually super wrong and you should not listen to me. So going back on that, we have a miss here and a miss here. So now let's just step through all of these examples that are not misses. So they could be misses or hits. It's unknown for the actual cache. Sorry about that. So the first thing to step back and think about is how many sets are in our cache right now. So our our set associativity is two ways. And that means we're using this set up here. So that means we have two sets. So my first question is, how do we fill out up to this point? Which addresses go in which set? Yeah, so 0x4 and 0x15 go in set 0. And the reasoning why we can make this conclusion is because the set index is a 0 right here. And the way it works is our block offset is the rightmost bit, and our set index is the next set of bits. And so we know that our block offset in this example was 1, and our block offset bits were 1, and our set index bit were 1. So that means the least significant bit would be our block offset bits, and our set index bits would be the next set of bits. So now that we have what our cache looks like, will 0x17, will this address be a hit or a miss? So actually, this set would be a hit because first we're going to look up in set 1. So we're going to look up this tag in set 1, 0000101, and we see it right here. So that means it's going to be a hit. And the next address we're looking up is the following address, 0x14. And the first question whenever you're doing these lookups is figure out which set it goes into. And we look at the set index bit and we see that it has a 0. So that means we're going to look inside set 0 for this tag. And we see it right here. So that means this is also going to be a hit. Now we have the address 0000. So we see the set index. We look at set 0, and we actually don't see that tag. So now that we're using the least recently used policy, this is a miss, which element should get evicted? Yep, the first one. So we're just going to cross this one out and add in that 0 to the bottom. Okay, so now that we have that miss covered, where does the address 0x05 index into? Which set would it go to? Yep, it would go to set 0. So right here. And now we're doing a lookup in set 0 for this address. And do we see it? Yeah, so 0x05 would be a miss because we actually don't see it in our set 0. It actually just got evicted. And now we have our, so in this specific case, since the infinite cache miss hit, but the fully associative and actual cache missed, we'd classify that as a capacity miss. Next, we have the address 0x07. And so this would go in set 1 because the set index bit is 1. So now we're just doing a lookup for the address 0000001. And do we see that in our set 1? Yes. So as a lot of you said, this is a hit. So this is kind of surprising because our fully associative cache missed it, but our actual cache hit. And that's just because of the way our data access is worked out. So we see that this is actually kind of unclassified. If the infinite cache hits and the fully associated cache missed, and if the actual cache hits, we actually don't really classify it as a type of miss for 3Cs because our actual cache hit. And then next, we know that 0x24 is a miss. Which set do we need to add that address to, and which address do we need to evict? Yeah, and like the really big reason why it's not a capacity miss is because in our actual cache, we had a hit there. So we don't really classify it as a 3Cs miss. So why is the blocks offset not used / when would we use it and need to use it in sets? So the reason why I'm kind of glossing over the block offset is because the block offset is just a way. So taking a step back, the way caches work is we have our address, right? We have like in this example, we have 8 bits of our address. And the really important thing we know is that the addresses, I guess, for example, in this problem, the address is 0x04 and the address is 0x05 share the same block, right? Because our block sizes are 2 bytes. And because these share the same block, we need to use some way to determine which actual address we want. Do we want the first one or the second one? And so that's what this block offset at the end is used for. Did that make sense? Okay, so it would, and then going back to the question, 0x24, that's not the tag, that's the address, but the tag associated with that would go in set 0, and that means we need to evict out the least recently used, whatever that number is. And then finally, we have our last 3. So which set do we need to do a lookup in for 0x06? Yep, set 1, and is it a hit or a miss? So it's a hit. And because it was a hit and it was in set 1, we just do an update of the least recently used value. So that means this one is now highest priority, or lowest priority for being evicted. And then now we have the memory access 0x01. This is in set 0. And do we have that address in our cache? Wait, did I mess something up? I think I might have. So the answer key says that is not a hit. I think it's probably a way, the reasoning why it's not a hit is because I messed something up with set 0 in the priorities. I think we probably should have evicted a different value. That's my bad. So I guess this is one reason why these questions are really, really tedious, because you have to be, even if you have hits, I bet somewhere along the line in the recording, you can figure out where I messed up exactly. But I'm guessing what happened was I forgot to update the priority for a hit and update set 0. So what we're actually going to do, this really sucks, but we're going to have to start from basically the beginning because I don't know where I messed up. So we're going to go through this really quickly. So set 0 and set 1. We have the address 0x04. And so that means this one looks like this. This one looks like this. And because these two are hits, that means we update the priority of 0001 and 00, or basically these two things, which are already the highest priority. Next, we have a miss with 0000, and that's going to go in set 0. So we cross this one out and add it to our cache. And the important thing to note is that now, what was it? Address 15 is now the lowest priority and is highest priority to be kicked out. Next, we have address 0x05. So that's going in set index 1 or set index 0. And since we actually don't see that value, that's a miss. And then 0x07, we look up in set 1, 0001. So that means we update the priority of this. And then address 24, we don't see that address, so we have to evict out this value right here. Oh, wait, my bad. So since address 0x05 was a miss in set 0, this has to be added back to the cache. I forgot to add that. That's probably where I went wrong last time. Oh yeah, everyone said that in the chat. So 0x05, that one's a miss, so we need to put it in the cache. And now 0x24, that's also a miss, so it needs to be placed in the cache again. And that means that address 0 is evicted. So this was a hit, I think. So 0x06 needs to be updated. So this is fine. I think this is still the highest priority, so that looks good. And then now we have address 0x01, which now isn't in the cache because it got evicted earlier on. So this would be a miss. And then finally, we have address 0x04, which is also a miss because we can't find that tag inside set 0. And now because we had a fully associative hit along with an infinite cache hit for these last two, it's going to be a conflict miss as opposed to a capacity miss. So sorry about the hiccup in the end, but I think we did the problem. That's one reason why these problems are really, really tedious, and I hope we don't give you a problem that's this long on like the midterm or on the final or homework. Does anyone have any questions about the problem we just did? I'm still confused as to why the second to last one is a miss. So why 0x01? So the reason why that one was a miss is because I messed, like, it was 0x24 ever put in. Oh shoot, yeah. I think I also dropped that one too. So yeah, 0x24 should have been put in here. Or wait. Oh. Okay. So I think was 0x24 ever put in? I think I did put that one in. Shoot. Yeah, I think I messed it up for a second time. So that's really, really cool. But still confused to why the second to last one is a miss. So if we just look at set 0, I think that's the easiest way to go about this question. So we know that this is set 1, so it's irrelevant, along with this, 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 and this. So set 0 has, oops, it has 0x04. We also know it has 0x15. Then we see it has 0x14. So that's just going to update this one's priority. And then it has 0x00. So that means we have to evict this value. And then we have 0x05 again. So we evict 15. And then we have 0x24. So we evict 0x00. And then we have 0x01. So we evict 0. So the reason why the second to last one was a miss was because 0x05 should have got evicted. I forgot to evict it on the first run through. So yeah, these questions can get very confusing very quickly if you aren't super clear with your notation and then also super diligent about evicting and also updating values. So yeah. Now, does anyone have any questions about the question, I guess? All right, I guess then if no one has any questions, I'll stop the recording and I guess good luck with the rest of the class.